consider now a second example where the differential equation is y prime equals 1 minus y square. This is a first order nonlinear differential equation. Initial condition is 0 at y 0 is 0, and the time interval is the same as what we had before, between 0 and 2. This problem, you can sort of think about how to solve this. It turns out we can solve this analytically. There's a little bit of work involved, and we have already learned these methods to solve this before, and you should be able to demonstrate that the exact solution is a tangent hyperbolic function in time. YE is hyperbolic tangent of time, and that satisfies this initial condition and this differential equation. So we can use it to have absolute estimates for error. And so again, we apply first order and second order Euler method with different time steps and compute the error. We plot the function, we look at its behavior, and here we quantify the error in this table. And so if you look at the numbers in the first set of rows here in these columns, we have the 2 norm of the error, 1 norm of the error, and the infinity norm of the error, which means the worst error over the interval. And again, we would notice that as we reduce the step size by a factor of 2, error is approximately reducing by a factor of 2. You can see, and that is something that is easy to see when you write these numbers down and sort of imagine multiplying this by 2, and you would get something close to this, and multiply this by 2, you'll get something close to that, and so on. So that trend is seen not just for a specific norm like 2 norm, it's seen throughout for any norm that we have. So as long as the solution is a smooth function, all of these norms behave in the same way. And going to second order Euler, we again see the same improvement that we had seen for the linear differential equation from this at step size of 0.2, we have error of 0.027. That drops dramatically to 0044, and that drops by large factors, by quadratic factors, a factor of 4 roughly, as we go to smaller and smaller step sizes by factors of 2. And that's seen again throughout for all the norms that we can examine here. So this is a behavior that is also observed for higher order schemes, and there are some very popular higher order schemes like the Runge-Kutta scheme, the fourth order Runge-Kutta scheme, and so on. And so you may wonder, why is it that one is interested in higher order schemes? And that is because in many problems it is not enough to have a few digits of accuracy. So here, for example, in the best cases here for this nonlinear problem, we have 3 digits that are correct. The 4th digit is wrong. And so this is when we have integrated the solution out to a time of 2. What if we are interested in times that are much larger? We can look at this problem, and you can verify this yourself, that if we increase the window over which we are trying to describe the solution, this error, overall error, will degrade. And so depending on the application, we may be interested in long-term predictions, and then the error requirement for long-term predictions would require that these, in order to keep it within some acceptable tolerance, these numbers will need to be much smaller. So higher order methods are therefore necessary. And also, for example, you may think about if you are launching a spacecraft that is going to land on Mars, we need to be able to precisely predict the trajectory, and it's going to go a long distance away, and so local errors can accumulate. And so in order to ensure that the behavior we seek is in fact followed by the system that we are deploying, it is necessary to have very accurate solutions. And so higher order methods, and methods which have time stepping, which is local, based on behavior of the solution, where some phenomena that are occurring at a rapid rate, we want to reduce a step size there to accurately describe that transient, and where things are changing slowly, we have the freedom of increasing the step size there, and so on. So there are these generalizations of methods that can be practically used to reduce the overall cost. So this is a general behavior that can be exploited for broader problems.